Hi, we are Team 106, and this is our third checkpoint presentation for our project Mechaturtle. I'm Aiden.
I'm Richard.
I'm Glenn.
And I'm Enoch.
Alright, so for our mission statement, our thing was we will provide a tactile robot to teach kids and adults the fundamental principles of anisotropic motion and how it can be used in realistic environments. And as you can see there on our right, we have a cute little photo of our handy dandy little turtle. Alright, now here's our figure of design. So we implemented and improved a few changes from our last model. So as you can see, we did cut out some holes in the shell, so we can now mount our buzzer, which is not a project requirement, but does add some fun functionality, and we can add our LED in the shell. Additionally, we carved our team name into the top, and we scaled it down a bit because our circuit board was actually smaller than we initially intended. Now I notice these supports here do like trees. The reason for that is because this is intended to be a resin 3D print to improve the quality of our overall final product.
Alright, this is our overall block diagram. This is the whole part, and if you go to the next page, it's going to show the PSOC, which we worked on together as a group. And if you go on to the next one, this is the voltage regulator. Richard worked on this section. We didn't have that many changes to it, so it looks the same as the original one. And if you go to the next one, the distance sensor with the buzzer and the LED. Aiden worked on this, and it also didn't have that much changes from the original design. And then if you go to the next one, the motor and the motor driver, Glenn worked on this. We realized that we needed two separate sections for each motor, so we added that part. And then the next one, we have the op amp and the photoresistor, which I worked on, which was also like the same as the original part.
Alright, so this is our hardware implementation. This is the circuit schematic we use. And there weren't really that many changes to it. Everything is essentially the same as from the previous checkpoint. Here are the final PCB designs we used. You've got the one on the left is the top layer, and for the top layer it was mostly just traces used for power. That's why they're a lot thicker. Then for the right, those are mostly signal traces, and as you can see they're a lot thinner as well. Both planes are ground planes because we found it easier to just use both as ground instead of having a power plane and a ground plane.
So here is our software implementation. So first we have our initialize statements. It's basically just to initialize the system, make sure it's all good and running. We have the basic UART for RX and TX to be able to read our values and just to make sure everything's running. So then next we have our main loop. Basically we have the starts that you need for the sensors, for the buzzer to make sure everything's working. And then if we go into our outputs, you have if the photo is greater than 0.5, that means that it is not flipped over and it's currently steady on the table. And then we go into the distance sensor. So if the distance sensor has a greater than 600 millisecond response time, that means it is not in any immediate danger, so it proceeds normally. The green LED is on to let us know that the turtle is very happy. If we get in between 300 and 600 millisecond response time, then we know that the turtle is in sort of danger, so the LED will start to flash, the buzzer will emit a light sound, just to let you know that something's about to happen. But as soon as we get into that 300 millisecond range, then the turtle is in immediate danger. So the motors will stop to prevent him from getting harmed, and a loud annoying buzzer will go off, and then a red LED will go off to let us know that he is in danger.